Okay.
Let us begin. Okay, so. A short topic, and then we'll actually get into the topic that people actually think about when they start thinking about calculus. So we're going to talk about derivatives today. For that, maybe let's just maybe run through one of these quizzes really quick so we can see what's going on. No, I don't want to see. Yeah, you'll definitely see limits on your test, both in the picture version and the expression version. So you want to make sure you know how to deal with it. Usually when it comes to those problems, you want those problems to be the ones that you actually get. So I'm doing version B here. So version A is similar, but not exactly the same problem. How'd you do this one?
You factor.
Factor. This was that one where you needed to do some work.
I'd rather do it like
This is x minus 5, x plus 5. What is the top factor?
x plus x minus 5. X plus
5 and 1, minus and minus.
no, plus. No.
No, they both need to be minus, right? Because that minus 1 times minus 5 gives me positive 5, and minus 5 minus 1 gives me minus 6. You notice that this cancels, so now I can actually plug in x equals 5. So it'll be 5 minus 1 over 5 plus 5. That's 4 over 10.
That's version A.
This is B.
Wait, no, I got negative 5 then.
I don't know what your version, it depends on what version you had. So this is 1A. In B, we had the limit as x approaches 1 of x squared plus 5x minus 6 over x squared plus 1. How'd you do that?
Just plug it in.
Just plug it in. Get 0. C.
Right.
Limit as x goes to minus 2 of 6.
6.
6. D. Right? Like no work, like most of them. This is like the hardest one out of all of those. If you were like doing a bunch of calculations, I'm not sure what you were doing. Most of them are just like, oh, that's just this, it's just that. Okay. This one requires a little bit of insight, but you could. Negative infinity? Why did you say that?
I did a special technique.
Right, because the graph, right? So you know y equals 1 over x looks like this. So if your y equals 1 over x minus 3, it's just a shift to the right by 3. And so now you look at what's happening as you get to 3 from the left, and you see negative infinity. You could also do something like plug in a number very close to 3 but from the left. So like 2.999, you'll realize that this would approach 2.999999 minus 3, you would get like 0 with a slight negative charge. Right? So it's not 0, it's close to 0, but it's on the negative side. So you end up with a positive divided by a negative, and it shoots off to infinity.
So sorry.
7 minus x over 4x. Why'd you do this one? Just plug it in. F. 4x squared plus 2x plus 1. What is that? 0. Bottom hidden. What is that? Negative 4 over 3. Ratio of leading coefficients. 4 minus 3x to the 7th over 4 minus x squared.
Infinity.
Well, we know it's infinity, but what does the sign tell us? It's going to negative infinity, so the x to the 7th is negative times a negative, so the top is a positive, divided by a negative, so it's negative. 2. What's the equation that defines continuity at A?
From the top, if you substitute the negative infinity to the square root,
Right, it'll become positive, and then you multiply by a negative sign in front. What's the equation that defines continuity?
F of A, it should be equal to the limit as f of x, wait, x.
Should be that. I mean,
Yeah.
kind of always do it the other way around, but it's an equation, you can write it any order you want. Yeah, so that was that. So you'll see, like, well, this is the only one that required work. All the other ones, you can either just plug in directly, or you just notice a pattern, right? And the limit problem should kind of be like that. So the most work you should be expected to do on a limit problem is like some factoring, but everything else, based on what we did last time, it should take you like no steps to actually do one. And I'm probably not going to go over this because this was exactly the same graph and exactly the same problems I asked you on the last quiz. So this is just a repeat problem. And part D was in the bonus of last quiz. I just moved it up to being in this quiz. And basically in this one, it was continuous for B because this equation holds. You had f of 2 was equal to 3, and if you look at the limit as x approaches 2, you get 3. And I think in version A it was not, because there was a hole here, so the answer was no, it's not continuous because f of 2 wasn't defined.
There's no hole.
Huh?
I just wrote because there's no hole.
Because there's a hole?
Because there isn't.
I
had B. I wrote it's continuous because there's no hole.
Because there isn't a hole?
Yeah. I don't know. Just let me get that one.
I'll give you half. If saying there's a hole to say it's not continuous is okay, right? But to say something in terms of what it isn't, that's kind of, because it's not, the hole isn't the only thing that would make something discontinuous. I don't know. I'd probably give you a half for that. So it's like someone asks you, what's a dog? Well, it's not a bird. Like, it's not really, it's not really saying anything. But yeah, you notice there's a break or a hole, or you notice there wasn't a break, I guess. That counts for something, but probably wasn't the thing I was looking for. I'd expect you to say, oh, this equation is true. The same equation that I asked you in the prior lesson. We are going to continue with 2.4. We're going to talk about limits a little bit more, but in a specific context, we're going to talk about asymptotes. Now, these describe a general idea, but we only care about two kinds, okay? So, an asymptote is a curve, right? So the curve could be the equation of a line, could be a parabola, could be whatever. It's the equation of some graph. That is a curve that a function approaches as the x or y coordinate. Approaches some x infinity, right? Don't really need to know that definition. We only care about two. We care about two kinds. One, vertical asymptotes. This is when your asymptote is a straight vertical line. Right, so for example, like the graph y equals 1 over x has a vertical asymptote at x equals 0. So you'll notice that if you look at this graph, look like that. Notice that as you're approaching 0, your y-coordinate is shooting up to infinity, and what your function is doing is it's approaching that line. It's approaching the line x equals 0, so this definition is fulfilled. So x equals 0 is the y-axis, and your function is approaching that as the y-coordinate is going off to infinity. Right? It also has a horizontal asymptote, which is the other one we care about. You'll notice that there's a horizontal line that the function will approach as your x goes off to infinity. So we care about vertical and horizontal asymptotes, and I'm going to tell you how to find each of them. Horizontal asymptotes. There is like y equals 1 over x squared as a horizontal asymptote. Y equals 0. So again, if you look at this one, you notice if you're worried about is there a horizontal line that this function is approaching, that line would be y equals 0, which is literally the x-axis. You realize the function is just approaching this line as you go off, as the x-coordinate goes off to infinity. And this would be the equation of that asymptote in respectively. So the vertical asymptotes, they're always going to be like this. So these are always, so a horizontal asymptote is going to be a horizontal line. You just need to identify what that line is. What is the y value that if I drew a horizontal line, my function will approach that guy. And for these guys, it's going to be a vertical line. So the only two kinds of asymptotes we care about are ones that can be described as y equals a constant or x equals a constant. Is there a vertical line that our function approaches, or is there a horizontal line that our function approaches? Now, how do you go about figuring out each? Let's deal with one at a time. Now, I'll tell you the definition here, but the definition is actually probably not how you want to think about it in practice, because there's going to be a specific situation in which you want to find these. But the definition will be the following. We say x equals a is a vertical asymptote. Of f of x if the limit as you approach a of the function is infinite. So if there's a number that we can pick where as you take the limit going to that number, you get either plus or minus infinity, that's called a vertical asymptote. Right? So you'll notice something like, if I take the limit as x approaches 3 from the left of, let's look at this guy again, we got negative infinity. Right? This is kind of saying that x equals 3 is a vertical asymptote. Right? The fact that I approached that number and the answer was infinity shows me that there's a vertical asymptote there. A is a finite number. So anytime you approach a number and the answer is infinity, if you look at, and this can be a one-sided number. So if you look at, again, x approaches 0 from the right of 1 over x, that answer will give you infinity. This would mean that x equals 0 is a vertical asymptote. Let's call it just. Now, I probably wouldn't check it in this way, so let me give you a nicer way to think about vertical asymptotes, because they're usually going to ask you about it in only one situation. So the important part is you will only be asked so that can simplify matters for us. We don't even have to look at a limit here. You'll only be asked about vertical asymptotes. Of f of x, where f of x is a rational function. Right? Now that makes things a lot simpler, right? So remember what rational functions are. This means that your f of x is, it looks like p of x over q of x, where p, q are polynomials, and q is not equal to 0. Okay. So these are examples of rational functions, but also you can look at something like x squared plus 3x plus 2 over x squared minus x minus 2 is also a rational function, right? So you just take a ratio of two polynomials. So usually they're going to say, okay, here's a function, they'll give you a rational function, and they'll say, find its vertical and horizontal asymptotes. Now, when you're looking for the vertical, this is the easy way to actually do it. You don't even have to think about limits, really. To find vertical asymptotes. So this is the important part. If you, to remember one thing, this will be the thing to remember. To find vertical asymptotes. Find the x values where the denominator becomes 0 and the numerator is not 0 at the same time. Or to be more specific here, specifically
equals to
the factors that make the denominator equal 0 will not be cancelled when simplified. Will not be cancelled when simplified. So that's the first thing you want to do. Identify where the denominator will reach 0 for a rational function. Now, if you're in the case where the top factors into something that cancels one of the zeros, then that thing is not an asymptote anymore. That's how you get a hole, right? So if you can actually cancel the problem, holes are what are a result. But if you can't cancel the problem, it means your graph is going to either shoot up to infinity or shoot down to negative infinity. And so pretty much to find the vertical asymptote, all I need to do, find where the denominator is 0 and make sure that nothing in the numerator is going to cancel those factors. Do I want to do examples now or do I save them? I'll save examples till the end. Because we'll find both the horizontal and the vertical in one shot. So that's the important thing. So when it comes to vertical asymptotes, that's what you need to remember. And you need to remember this, not because it's that easy, but because you're only ever going to be asked about this specific situation. In that situation, that's all you have to worry about. So you're going to just factor the top and bottom. Once you factor the bottom, you'll identify the x's that would make the denominator 0. All you're going to do is check that no one in the top is going to cancel all those guys. Anyone after simplifying, if they're still there, that's the vertical asymptote. Anyone who gets canceled would be a hole. Okay. So let's try it. Because that will help you answer to the bonus quiz problem. factors in the denominator that are cancelled upon simplification tells you about you should know that that's a nice thing. They might ask you about holes. They don't do it often, but I've seen it before. So pretty much any factors in the denominator that's going to create a zero that doesn't get canceled creates a vertical asymptote. That's the short story. We'll do some examples after I describe what happens, how you find horizontal asymptotes. Well, let's not just do the definition, because that's just me regurgitating the thing. Let's actually say how we find it. To find horizontal asymptotes, compute these two limits. So this one, you can't get out of doing limits, but the limits will actually be nice ones, because they're going to be limits at infinity. And we know that there are tricks to doing this when your f is a polynomial. It should be an answer that you can easily figure out. Now, in general, for a rational function, these will both give you the same answer, but I would probably ask you to think about both in the case that they might give you a piecewise function or something like that, where on the right side and the left side it behaves differently. You really want to know what's going on as your x gets infinite in either direction. But they'll ultimately give you the same answer if you just have a rational function, it's not a piecewise function. So you'll compute these two limits, right? And you'll be able to tell what the answers are. If the highest power is on the bottom, they'll give you 0. If the highest powers are the same on the top and bottom, then you'll get the ratio of coefficients. If the highest powers on the top, you'll get plus or minus infinity. Now here's the thing. For horizontal asymptotes, you ignore the infinity case. If these give you a finite value, right? So it has to be 0 or just some number. Say k, then y equals k is the horizontal asymptote. So you compute this limit. If you get a number, let's say you find this limit and it's 5. Y equals 5 is going to be a horizontal asymptote. That's just it. Whatever the answer is you get, as long as it's a number, y equals that number is going to be your horizontal asymptote. That means as x is approaching infinity, your function is approaching and leveling off at 5. And that's the definition of an asymptote. That's pretty
like the K is
HA. That's short for horizontal asymptote. And that's pretty much what you need to know here. So asymptote is just a line or a curve that we're approaching as you go up to infinity. The two kinds you need to know about are vertical asymptotes and horizontal asymptotes. For the vertical, figure out where the denominator is 0. Make sure that those factors aren't canceled when you simplify. And those x values, the equation that those x values will give you the vertical asymptotes. For horizontal, you compute the infinite limits. If you get a finite answer, y equals that answer is going to be your horizontal asymptote. that's pretty much the summary. I should mention something just in case someone throws a graph into the mix and asks you about these. In general, a function may cross its horizontal asymptote, right? So for a function to, let's say, here's your x and y, and let's say here's a horizontal asymptote, y equals some value. In general, it shouldn't be weird. You shouldn't think of it as weird if your function crosses this line and eventually levels off, because you really only care what's happening eventually when it goes off over to infinity. So your function can cross the horizontal asymptote, maybe in several points. You shouldn't think of that as something weird or strange. It is strange to cross a vertical asymptote though, because remember we said in the situation that we're thinking about, vertical asymptotes happen when a division by 0 happens. So usually you're never going to cross a vertical asymptote. In general, you cannot cross a vertical asymptote. When f is a rational function. Because as I said, those guys occur when the denominator is 0. It won't happen that would be a thing. So you can probably have a strange case, which I don't think this will show up, just in case, you never know. A rare exception to this rule say complicated piecewise functions. Okay, so for example, if someone defines a function like it's 1 over x as long as your x is not 0, but we define it to be 2 when x is 0, then this graph is going to look like this. It's not 1 over x will never touch its vertical asymptote because a division by 0 happens there. But here they're just like, okay, we're just going to fill in this point. So technically your f touches the vertical asymptote, but it's not a very typical case. It's like someone had to alter something, right? But in general, a rational function on its own, it's never going to touch a vertical asymptote. So that you should be aware of that. So if you have a very simple function, it's a rational function, and maybe you have to identify a graph or something, you can pretty much rule out anything that touches the vertical asymptote. So vertical asymptotes, you won't touch them. It's not weird to touch a horizontal asymptote. So, but the vertical ones occur from division by 0. So in general, you can't touch them unless someone tweaks something. Right? Okay, let's look at some examples. And this will take care of the bonus on the quiz. Find the vertical asymptotes and horizontal asymptotes of the following. that's pretty much all we wanted to cover from this section, so it's a very short section. Now, some things are in here that I didn't talk about. That's because we kind of talked about it before. I talked about how an asymptote can help us draw a graph, but I've actually sketched word graphs like these in a previous class. So you should read through this, maybe read through the notes where I actually did sketch some rational functions, just for an added level of understanding there, because sometimes matching things to graphs is also an issue. Let's actually throw in some of the quiz problems here as well. So this is bonus for 7A. Bonus for 7B. We're going to do these numbered. So you might just be, here's a function, find a vertical and horizontal asymptote. It could also be the case that they'll say, okay, here's a function, which of these is a possible graph? And one of the first things you would do is identify the vertical and horizontal asymptote and try to match them up with the graphs. You'll see problems like that in the review for the next test. Let's do 8. So your f is equal to x squared, or x squared minus 4. Let's talk about V8s. What are the vertical asymptotes here? Plus or minus 2. So you say set denominator equals 0. This is x squared minus 4 equals 0. So you get x equals 2, or x equals minus 2. And notice neither of these will cancel, right? Because your f would be x squared over x minus 2 times x plus 2. You can't cancel any of these, so that's your answer, right? What about the horizontal asymptotes? Well, for the horizontal asymptotes, you find the limit as x approaches infinity of the function, which is?
It's going to be 1 divided by 1.
Plus 1, right? So, and this, notice it'll be the same for plus or minus. You'll get 1 in either case. So this means y equals 1 is the horizontal asymptote. So let me just remind you, I probably won't do this for all of them, but here's kind of what that would mean for a graph. So the vertical asymptotes, these are just the vertical lines. They have equations x equals 2 and x equals minus 2. So these are vertical lines that your graph will not touch because division by 0 happens there. We also have a horizontal asymptote, y equals 1. Right, so what you'd realize, there'll be a skeleton on the graph, right? There'll be these guidelines. So you know that as you're going, x is going off to infinity, your graph should be settling at 1. It will not touch these. We can also know from the intercepts that this actually passes through 0. So what we can do now to figure out where the graph is, we can actually test points. So if I plug in something like minus 3, right, into this function, the top is always going to be positive because it's a square, so I'm just going to look at the bottom. This will be a negative times a negative, so that'll be positive. Right, so it's up here somewhere. And plug in a number here like minus 1. That will be negative, that will be positive, that's negative. Plug in a number over here like positive 1. That'll be positive, that'll be negative, so it'll be negative. Plug in a number like positive 3. That will be positive. Now this one actually doesn't touch the asymptotes. This one means it has to stay negative, but it never touches that. But because this is an asymptote, I know it has to approach it. Similarly with this, it will approach that. Turns out the graphs up here would approach this as you go up to infinity, and it approaches that as you go up here. The graph's going to look like that. Now, we looked at this specific example before. You might ask, well, how do you know it didn't cross here? Because we actually set this equal to 1 and we show that it had no solution, so it never actually touches the 1. So it's positive and it always stays positive. This is the only x-intercept, so it never comes down and touches here, and it never crosses that blue line. So if it's positive, it has to be in the upper part, right? And so that could be a thing. So they might say, oh, here's the function, identify the graph, and they'll give you a bunch of choices. They'll have something that looks like that, and then they'll throw in another thing, probably looks like that, and then they'll throw in something that looks like this, and then, right, they'll give you a bunch of options, right? But then, once you find the asymptotes, and you know, oh, there are 2 vertical lines that this thing can't touch, right? So it definitely eliminates that option because there's only one such line. So you wouldn't even, that's not the answer choice. Both of these would have those situations. Right? But then you realize, oh, the intercept has to go through the origin, so it's not this one. So then you start worrying about this one, and then you realize, oh, it should be negative here, so it has to be this graph. So if they gave you these 4 choices, you ultimately settle on this one as the right answer. Because, and also for this, neither of these you would choose because they don't actually have the horizontal asymptote. Right? There's no horizontal line that they're approaching. These approach 0. So this example of this graph would get close to 0 as you're going up to infinity, and it gets close to 0 as you go up to infinity here. So this has a horizontal asymptote of 0. This also has a horizontal asymptote of 0. But your horizontal asymptote should be 1, so you know you should be leveling off of here. So that's another kind of problem, right? So whenever you'll see something like this show up, it'll either be the case where they say, here's a function, tell us what the vertical and horizontal asymptotes are, and then you have a bunch of answer choices. Another thing that you can look at, they can tell you a rational function, and then they can give you some choices. What is a possible graph of this function, right? And you just knowing about the properties of where a vertical asymptote should be, where a horizontal asymptote should be, where the intercept should be, you'd be able to, by process of elimination, eliminate all the wrong answers and end up on the right one. So that's kind of how a graph problem can come into play. But I'm not really going to graph the rest of them. I just wanted to kind of mention that that's a possibility. And you'll see problems like this in the old finals, so you can get some practice from those, as well as there are probably some in the homework as well. But as far as the actual calculations go, any questions here? So just know, vertical asymptotes, find where the denominator is 0, make sure nothing in the numerator cancels them, that's your guy. Horizontal asymptotes, find the infinite limits. This is going to be easy, right? Because you know there's only 3 choices based on where the highest power is. And y equals, anytime you get a constant number, y equals that number is going to be a horizontal asymptote. Your graph will approach that line as the x goes to infinity. So let's look at B. So one thing you'll notice, you can kind of factor the top, but nothing's going to cancel, obviously, right? So in terms of the vertical asymptote, this means the 2x plus 1 equals 0, so your x equals minus 1/2. That's your vertical asymptote. That makes the denominator 0, and there's nothing to cancel that from happening. For horizontal asymptote, you're just going to find the limit as x approaches positive or negative infinity of this function. What's that? Huh? What's the answer?
It's infinity.
It's infinity. So basically you'll say here, there's no horizontal asymptote. Right. To be a horizontal asymptote, you have to get a finite number here. It has to be a number. Right? And then you'll say y equals that number is the horizontal asymptote. If you get infinity, that's the situation where you don't have a horizontal asymptote.
How did you get infinity?
Highest power is on the top. It's top heavy. Right. So remember the three situations. Highest power on the bottom, you will get 0. In that case, y equals 0 is the horizontal asymptote. Highest power is the same in the top and the bottom, goes to the ratio of the coefficients. That will also be a number, and y equals that number is the horizontal asymptote. The moment the highest power is in the top, there's no horizontal asymptote, because you're going to get either plus or minus infinity. So ultimately, this is the quick way to look at it. Where's the denominator 0? Does anything cancel it? No? Okay, that's the vertical asymptote. Has to be x equals, right, because it's vertical. For horizontal, find the infinite limit. You'll have one of those three cases. It's either 0, the ratio of the coefficients, or infinite. In the infinite case, none. And all the other cases, whatever the answer is, y equals that is the horizontal asymptote. Okay, this one, vertical asymptotes.
Square root.
What do you do for the vertical asymptote? Right, you said x squared plus 1 equals 0. That has no real solution. So, no vertical asymptote. What do you do for the horizontal? Find the limit as x approaches infinity of the function. What do you get? You get 0. Y equals 0 is the horizontal asymptote. Whatever this graph looks like, I'm not going to graph it, but it has no vertical asymptote, but the graph settles at y equals 0 as you go to plus or minus infinity for the x. Vertical asymptote. Right. You said the denominator equals 0, no solution, no real solution anyway. This means no vertical asymptote. Horizontal asymptote.
There is none.
Right, you look at the limit as x approaches infinity. Highest power is on the top, no horizontal asymptote. So this one has no vertical or horizontal asymptote. Right? You don't have to have it. This one has neither.
Wait, why is that no horizontal?
Because you don't get a number,
Oh.
you get infinity. So to be horizontal asymptote, you must get a finite number. So when looking at the limits for the horizontal, the infinite case is the only one that gives us nothing. The other two cases will give us an answer. E is over there. 2x squared minus 5x minus 3 over x squared minus x minus 6. Okay, so that looks like the top can potentially do some damage, so let's simplify a little bit first. Does the top factor?
Yeah.
Be 2x and x, maybe 3 and 1. That'll give me a 6. That'll give me a 1. To get a minus 5, I need a minus 6 and a positive 1, and that works. Let's look at the bottom. I need two numbers that multiply by 6, get a negative 1. 3 and 2 seems to be it, with a minus 3 and a positive 2. Okay. So now, vertical asymptote.
-2.
Right, and that's the only one, right? Because notice the x plus minus 3 is going to cancel, right? Now what that means is that x equals 3 is a hole, right? There's a hole at that point, right? So technically a division by 0 happens, so the graph can't actually exist there, but once you're not at 3, this is just a fraction that reduces and your graph is going to behave nice everywhere else around it. So you'll have just a little hole at the point where x equals 3. So there's only one vertical asymptote here. There are two things that make the denominator 0, but one of them you can actually cancel away. The ability to cancel it away creates a hole. Right? So in terms of domain, it doesn't make anything better, but in terms of a graph, it goes from being an asymptote to being a hole. And what about the horizontal asymptote here?
2.
So I look at the limit as x approaches infinity of the function. Now you look at the highest part on the top and bottom is the same, so it goes to the ratio of coefficients. That's 2. That's a number. That's a finite number. So this means that y equals 2 is the HA. Questions on that one? So on the quiz, I asked you to identify the horizontal, the vertical, and the location of holes. So let's do that one, if any. So some canceling might happen here, so I'd probably start by factoring. X, 2 and 1, positive for both, works here. 3 and 1, positive for both, works here. Notice that this guy gets cancelled.
Which is the whole.
So from that we can say we have the whole at x equals minus 1. We have vertical asymptotes at x equals minus 3. We have horizontal asymptote at where?
At 1.
Y equals 1. Right? You have to write the equation. You can't just say 1. You have to say y equals 1. Because it's actually a line. It's actually a curve. But see, once you know what to look for, it's not so bad. You don't even have to write out the calculations. You can just, oh, that's going to be 0 and we don't get to cancel it. That's vertical. This is a 0. It canceled. That's a hole. Okay. Highest power is the same in the top and the bottom. That goes to the ratio of the coefficients. That's actually a finite number, so that's your horizontal asymptote. So, once you kind of know what to look for, it's not bad at all. X squared minus 3x plus 2, x squared minus 4x plus 3. Again, I see two quadratics. I'm probably going to try to factor them. Whenever I see something like this, x, 2 and 1 maybe both negative. In the bottom, 3 and 1 also both negative. You'll realize that this will now cancel. The things in the denominator that get canceled tells you where the holes are. X equals 1. Things that don't cancel in the denominator tells you where the vertical asymptotes are. X equals 3. And then you realize you're looking at an infinite limit. Same power in the top and bottom is the leading power. And so it goes to the ratio of coefficients, which in this case is also 1. So that'll be the answer. Pretty much it. Any questions on this?
How do you find a horizontal asymptote?
You find the limit
Oh my god.
as x goes to infinity of the function. And you technically, to be a purist, you find both as you approach positive and negative infinity. For rational functions, you'll always get the same answer. So that's what I did. Find the infinity, and I know for rational functions there's a trick. Highest power is on the denominator, it's going to be a 0. Highest power in the numerator, it's going to be plus or minus infinity. Highest power is the same, goes to the ratio of the coefficients. So you don't need any calculations here, you're just noticing the patterns. So there are calculations in the background, but for the most part, a problem like this you can kind of think of as a concept problem, because you don't really have to do many calculations. Once you kind of factor things, you should be able to just look at it and know what's going on. And yeah, that pretty much ends the section. Hopefully that wasn't too bad. Any questions before we move on? We're going to move on to something completely different right now. For a while it's going to involve a limit, but it's one very specific limit, which we'll talk about now. We'll talk about this for half an hour-ish, and then we'll take a break, and then we'll continue. I kind of want to do 2.1 and 2.2. I think they kind of flow better together as one idea. We're going to talk about the derivative and its properties. Now, I've mentioned the word derivative before. Let's actually specifically identify this guy. So one, recall, we are interested. Just one way of saying, I don't know how interested these people are, in solving what we call the rate problem. So I told you that calculus was invented to solve two problems. One was called the rate problem, and the other is called the area problem. So the rate problem is trying to figure out how fast one thing is changing with respect to another thing, right? So figuring out the speed of something. So how much distance is changing in terms with respect to time? That's speed, right? And so that's the rate problem. We try to figure out how fast something is moving. Do we figure out how fast one quantity? So you have two related quantities. You want to know, in terms of how fast they're changing, how fast is one quantity changing with respect to the other? So we're actually going to solve the rate problem. So that's ultimately the goal here. But it's a very broad and general problem. You kind of probably don't know where to start. So, as always, math people start with the simple things that they know how to figure out, and then they try to build up to a complicated thing. So here's something we know. This is also a bit of a throwback. We saw an interesting, there's a word interesting interpretation of the slope of a line when we were doing that section on the equation of lines. Right? So that was when I said, oh, imagine there was this object that it started from a position 0, and after 3 hours, it was 150 miles away. Right? We looked at that thing. Time in hours. And we saw the slope of that line was actually the speed of the object. So how do we find out how fast things are moving in general? We don't know, but in this specific situation, if we're looking at a straight line, we kind of know how to do that one. Measure the slope. The slope tells me how fast the y-coordinate is changing with respect to the x-coordinate, right? It's talking about the steepness, the rise over run. How much the y increases versus how much the x increases. That is, and this relationship is a measure of what we call speed. Right? So we're talking about the rate problem. We want to figure out how fast things are moving. This is one specific situation in which we know how to answer that problem. So this isn't general enough, however, right? Because what we're looking at, the functions we care about or the things we're tracking might not behave like a straight line. So how do we take this idea and apply it to anything else? So let's say to a function that looks like this. It's just doing whatever it is, right? And I want to know, okay, at this point, how fast is the y-coordinate changing with respect to the x-coordinate? So we kind of understand, okay, if it's a straight line, we know what we're going to do. But what if it's a curve? How do we deal with that situation? And the answer, somewhat surprisingly, is to think like a flat earther. Okay. So most of us know the earth is round. We've known for a long time. But of course, at the scale that we're at, sometimes when you look around, it looks pretty flat, right? That's the idea. Curvy things can look flat if you zoom in, right? So, yeah, this is doing a lot of waves, but what if I were to magnify this? Like I really just like blow up the picture, right? What's going to happen is, the more I magnify, that curve is going to start flattening out, right? So there's a slight curve here, but the thing is when you zoom in, if you get to a small enough scale, it can look pretty flat even though something is pretty curved, right? So here is this guy. And so the idea is, if we zoom in, curves may start to flatten out. And so here's the idea. The light bulb goes on. Okay. When it starts to flatten out, it will start to look like a line. And so now the question is, what is that line that it will start to look like, right? So we're imagining that there is some line here that I can create in such a way that if we zoom in, the function and that line will be doing almost the same thing, right? Now the curve is going to go away from the line eventually, but the more I zoom in, the more these two things start to look the same, okay? So now that was the idea. Approximate this flattening out with a line. So basically what we're just saying is, okay, this thing is curving, I don't know how to deal with curves, I know how to deal with straight lines. So what do? Zoom in to the point where it starts to look like a straight line. And then talk about, it starts to look like this particular straight line if I zoom in, right? So this line approximates the curve close to the point. And we call this line, it's called a tangent line. right? The word tangent means to touch. So we can say this line touches it in this one point, and it kind of looks like the function would look within a very small area. Once we're zoomed in close enough, right, kind of hinting at the word close here, once we zoom in close enough, the line and the curve, they're kind of doing the same thing. I can pretty much think of this curve as that line. And so now you get to idea 2. What you're going to do is you can define, you make a new definition. We will define the slope of the curve right? If there is such an idea, let it be equal to the slope of this tangent. So okay, here's a curve that I want to understand in terms of speed. I know I understand straight lines in terms of speed, but it's not a straight line. Okay, here's the solution. Zoom in till it starts to look like a straight line. What straight line would it look like? That red one. Let's call that a tangent line. That's going to be our approximation for the function. The more we zoom in, the more that line looks like the function. And it would look like it the closer we zoom into some point of interest. Any line that does that job we will call a tangent line. And what we will do is we will define the slope of the curve to be the slope of that line. And what does the slope of that line represent? The speed. It represents how fast that thing is moving. So basically what we're doing is we can talk about how fast the function is moving at this point by measuring the slope of this line that approximates the function at that point. Right? And the more we zoom in, the better this approximation gets. Right? So now there's the next follow-up question. How would we find such a line? More specifically, how would we find the slope of such a line? Because of course you'll notice pretty much the only thing you know here is one point. How do you find the equation or the slope of a line if all you have is one point? Right, we looked at all the equations that we have for lines. None of them we can figure out with only the information of a single point. Right? We can figure out the equation of a line if we have one point and the slope, but we don't have the slope. The slope is what we're looking for. The only other way we can figure out what the equation of a line is and what the slope is if we had 2 points. So that would be the answer. We need another point. Let's pick one. Almost at random. So okay, so here's the situation. Here's a function that I want to be able to and say that's my point of interest. I want to know how fast is the function moving at that point. I define how fast the function is moving at that point by whatever the slope of the tangent line is at that point. Because we saw that the slope of a line can be interpreted as speed. So create a line that behaves exactly like that function when you're close to that point, and its slope will give you the speed. But now you're like, how do we find the slope? Well, we should find the equation of the line, and then we can tell you what the slope is. Well, how do I find the equation of the line? I only know one point. We need another point, so we pick another point. So we go over here, and we pick some other point. And then you're like, okay. And say, well, yeah, we can now find the line through those 2 points. We can definitely find the equation of that line. And you might say, yeah, but that's not the line we want. Hey, but here's the idea. Then move this second point close to the first. That's the idea. Okay, so we created 2 points on this function connecting with a line. This is the point I care about, so I'm not going to move it. That's the point I care about. What we're going to do now is take this point and move it closer to this line, to the first point, right? So I want to move these points so close together, it's almost like they become the same point eventually, right? So, and you'll notice that as I'm moving this thing closer and closer, you'll notice something curious starts to happen. Now when I start connecting these with various lines, I connect this point to that line, then 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 connect this point to that line. What do you notice is happening to these lines?
It's going.
These lines are turning themselves into that tangent line, right? So I constructed some other random lines that I don't really care about. But by moving the second point that I picked close to the first, it causes that line to bend and move until it starts to line up with my tangent line. And essentially what I'm doing is I make that point so close together that going through those 2 points is kind of like going through that 1 point. And so now you might ask the question, well, how do we get close to something? A limit. That's what we've been talking about for the past 2 weeks. How do we actually come up with a mathematical machinery to actually make this thing happen? And the answer is a limit. It's going to be a limit. So here's how we're going to do it. And you might say, how do we make it close? And the answer is the limit. That's what's going to save us. The whole reason why we invented this idea, and we invented something that talks about getting close to a point but not actually being there, was for this purpose, right? We were kind of figuring out how fast a function was moving, and we kind of needed to make one thing close to another thing. And we had to talk about, well, what does that mean mathematically? The limit was that idea distilled mathematically. Okay, so now here's how you're going to start to set it up. Let's pretend that x is the point I care about. And let's call this function f of x. So this is going to be f of x. And the setup is going to be the following. The random point that I picked in the first place that I'm going to start moving towards x. Let's say I measured the certain distance away that was, call that h. So this is now the coordinate x plus h.
And that's what
And so now this over here is going to be f of x plus h. So this was the first coordinate, x comma f of x. That was the first point. That's the point that I care about. Okay? So this is like my x1 and my y1. But having 1 point wasn't enough. Pick a second one. Okay, let's pick an x2 and a y2. And what we're going to do is move the x2, y2 close to the x1, y1. So essentially we can turn this new line, which by the way is called a secant line. The name for this line, the line that touches a curve in 2 points, is called a secant line. So pretty much, by moving this point to that point, I can transform the secant line into the tangent line. And essentially what you will notice is that we want the difference between these points to go to 0. So we actually want that to happen. And how do we actually get that to work? Well, we use a limit. And so let's actually start the actual construction. So that's the idea, the thoughts that went into developing this thing. But let's actually write it down mathematically. Let's get a bona fide mathematical definition going. So we can start by talking about the slope of the secant line, because that one we can actually measure. Right? Let's call it m secant. So m slope of the secant line, that's just going to be the regular slope equation, y2 minus y1 over x2 minus x1. So y2 minus y1 over x2
minus x1, and we get f of x plus h minus f of x over h, gasp. It's the difference quotient.
And this is why that's a thing. This is why in algebra and pre-calc they always ask you to do this guy. It's because eventually you come to calculus and you're like, oh, that's what it was used for, right? They wanted to make sure you know how to calculate this from a very early time because eventually it's going to be very important. It's going to solve what we call the rate problem. So that was the slope of the secant line, right? So the slope of this green line here can be computed by that. So now, if we want the slope of the tangent line, call that m subtangent. This would mean that the slope of the tangent line is just going to be the limit as h approaches 0 of the slope of the secant line. Okay? Because as these points start moving close together, the slope of this line is turning into the slope of that line. And so I can actually talk about the slope of the tangent line via a limit. And so what I'm simply going to do is take the limit as h approaches 0 of this expression. Now this innocent looking limit is responsible for half of calculus. It's a very important limit. It is what helps us to solve the rate problem. And because it's important, math people show their appreciation for something important by giving it a name. This limit is what we call the derivative. This is muy importante. Let's name it. And we call the name the derivative. And we, if y equals f of x, we have two main notations for this. One is the Newton's prime notation. It's Newton again. So if you want to talk about the derivative of a function, you use this symbol, f prime of x. Right? So it's kind of like an apostrophe, but a very ostentatious over the top one. And that represents the derivative. Okay. You also have the Leibniz notation. So Newton was British, Leibniz was German. It is believed that they both developed modern calculus pretty much around the same time. Newton was a little bit first, completely independently, but of course they always accused each other of copying the other's work. One of those old mathematical feuds. Leibniz decided to use the notation dy dx. Right? So this was kind of a play on the fact that we're using the slope. The slope is the change in y over the change in x. That is delta. That is the Greek letter delta, uppercase delta. So d for delta. So he decided this is what the actual slope is, but this, remember, is just an approximation of that. So he just put a lowercase delta, a lowercase d to represent that. And that was his idea. That is called the derivative. So we call this the derivative of y with respect to x. And that's the same, they mean the same thing. Just different notations of the same thing. A lot of the time I would write this one, or I'll just write something like f prime, because it's easier to write. And So these are called respectively. This is red f prime of x. And this one is red. If you're saying it, you want to sound like you know what you're talking about. dy dx. Okay? So no one says dy over dx or dy divided by dx. No, they just say dy dx. Whenever someone says dy dx, they're talking about this. Right? And they're talking about what we call a derivative. So that's a derivative. These are some notations. So let me finally write down the main definition of this section, just to put it all in one phrase. Definition. So this is something you should know. Let f of x be a the derivative of f with respect to WRT means with respect to x. That's identifying who is the independent variable, right? So this is the dependent variable, that's the independent variable. Provided it exists. Now this is a limit. It's possible that it does not exist, and we'll talk about those situations soon. So the derivative of f with respect to x, provided that it exists, is given by this limit. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. That is an uber important equation. That's just something that you know now. It'll definitely come on quizzes and tests, and it's something you have to recognize. So on the next quiz or test, I might ask you, use an equation to define a derivative. I'm talking about this equation. It's going to be this. This is the definition of the derivative. This is called the limit definition of the derivative. It's a very important equation. This is the answer to the rate problem. By considering this limit, we can talk about how fast one thing is moving in relation to the other. Which I'll give you those interpretations and then we'll take a break. Because that, especially for this class, knowing this equation is important, knowing these interpretations are important. Right, so remember, it's not just about knowing a formula, it's about knowing what the formula means. So when you look at f prime, of course you think of this as the derivative of f. From now on, you should consider derivative as a synonym for slope. If someone talks about derivative, you can literally replace it with the word slope. The sentence will maintain its meaning. Right? But the derivative is more general. When people use the word slope, they usually talk about the slope of a straight line. But when they mention derivative, that's an idea that can apply to various kinds of curves. But using it either way, you can talk about the derivative of a straight line. It's the same as the slope. And you can talk about the slope of some random function. It's the same as the derivative. These are synonyms. And what this is, it's the slope of the tangent line to f at x. We can talk about the, you can even think of it as a formula to find the slope. At x, you can think of it as the rate of change. The fancy word for speed, but more general in terms of velocity, of f with respect to x. You can think of it as how fast
y is changing with respect to x.
So for example, if your derivative is 5, you know that y is changing 5 times as fast as x is changing. Whenever x increases by 1 unit, the y will increase by 5 units. If x increases by 2 units, the y is going to increase by 10 units. It will grow 5 times as fast, and whatever number you get from the derivative tells you that. This is how fast this guy is changing in relation to that thing. So those are some common interpretations. And so with these interpretations, this can tell you the kinds of questions you can answer. So you might have a question that says something like, here's a function, find the equation of its tangent line. You're going to remember, oh, the derivative tells me about the slope of the tangent line. I should be finding a derivative. Okay? The problem's not going to tell you, oh, find the derivative. It's never going to say that. It's going to say something else. It's going to say something like, how fast is this moving? Oh, I should be finding a derivative. What is the equation of the tangent line at this point? Oh, I should be finding a derivative. They can say any of these things. What is the slope of this graph? They'll give you a random graph and maybe a formula. And then, oh, I should be finding the derivative. These are all different ways of saying the same thing. All of these phrases means you should be finding a derivative. Okay. We'll take a break. 15 minutes. Have some quiz to give back, Caitlin. Christine. Oh, stop this.